Hello everyone, in this video we will discuss the step 8, test the manual control and introduce the Ziegler Nichols method, the setting rule for the gain, integer, and the derivative, this setting rule. And the reason why I would like to use this video to introduce the manual control, that's because, as we know, the PID controller, normally we will run the PID controller in automatic mode. However, before your system fully automatically run, you better set your PID controller into a manual mode and manually control your valve or actuators and find out where is your system operating point. For example, when this system start to manufacture its product, so this system work around 40 centigrade. To achieve this 40 centigrade, the manual output, this PID output should work around 25%. So that means for this system, that 40 centigrade, that is a working operating point. And to achieve this 40 centigrade, that 25%, that is the PID output operating point. So that is the first, the production oriented. And the second, that is our control range oriented. And my system can still output from 25 to 100 or from 25 to 0. So that means my controller has a full range, can control this process. Sometimes for some system, for example, if my system still want to control the system work around 40 centigrade, however, maybe my controller already output 90% or output 10%, that means my controller almost cannot fully control this system. So you need to rethink your system design. Maybe your actuator is not fully enough. Maybe your process, for example, the tank is not large enough, or maybe the pipe is not wide enough. So you need to rethink your process. That's why before we fully run in auto, we better manual control our process. Using the manual control, you can basically find the behavior of your controller and your process. And also, I will introduce the Ziegler Nichols setting rule. Fortunately, in the Beckhoff website, they have an introduction of this Ziegler Nichols setting rule. If you saw the Siemens PID loop control series video before, in that series video, I introduced the Ziegler Nichols setting rule. And in that series video, I used the second method of the Ziegler Nichols way. That basic idea is we need to tune the gain only, increase the gain from almost 0 to a very high value till the system getting oscillation status. And when the system gets oscillation status, we record the gain value and the period of that oscillation. However, in practice, in some special case, the process cannot get this oscillation status because once the system gets this status, maybe the system is working under a one-way dangerous situation. So that's why the Ziegler Nichols method today I would like to introduce. That is the one common used method. Usually we call that the first method of the Ziegler Nichols method. The basic idea is we will give the output one step response and record the system step response and record 2 times within the trend. And using these 2 times, we can basically calculate the PID3 parameters. Okay, as I introduced, this Ziegler Nichols method, we can find out the detailed description from the Beckhoff website. Follow me, let's go to the Beckhoff website. Under this TL4100 CC3 controller toolbox, we can go to the appendix. And under this appendix, there's one section named the setting rules for the PID controllers. And it introduced 2 methods. One is this Ziegler Nichols method. One is this method. As we know, one common way to calculate the PID parameters, that is this Ziegler Nichols method. Usually, I will call that first method. So using this method, the key idea is we will give a system a step response. And then using this dash line, we will record the time at here and here. After this, we will use this table to calculate the PID or PI parameters. The TS, that is a time consistent of the control system, that is this area. And TT at the denominator, that's the die time of the controlled system, that is this value. So we will give a system a response And we will draw a dashed line, basically calculate this 2 times here. Also, we need to calculate this Ks. Ks means the denominator, that is a control output value, and the denominator, that is a step response of the process value. So we will find this gain value. So as we can see, to get this 2 value, we need to shift our PID controller into manual mode and control the PID output directly and give the system a response and check out the step response of a process value. And from the previous video, as we discussed, we already set up the online trend to monitor the set point input output of the PID. So we can shift the PID into the manual mode and manually control the output, monitor the input so that we can calculate that 2 times. Alright, let's go to the TwinCAD 3. Firstly, let's manually control the process, and then let's give a step response to this process. Okay, now this trend is working, and let's quickly review this program. As I introduced from the previous video, this is the online status. This simulated process is the operating point, that is the 40 centigrade. Its operating point for the control, that is the 25% value. Currently, the controller is working under the manual mode, and I give this process a 25% value. This system is working around 40 centigrade. Also, I will enable this noise to demonstrate if we are controlling one actual process, that process has a noise, how we can deal with this curve and how we can calculate that time. Okay, I will enable this noise. So after I enable this noise, we will see this process feedback, it has a noise inside, but basically it's working around the 40 centigrade. So let's go to the trend. And now this process, this dark blue, that is working around the 40 centigrade. We will see this. And the right curve, that is the control signal, that is the 25. Okay, the system is in a stable status. And let's set this manual control to a different value, and let's see what the behavior of this process value. And that is one cooling temperature system. Firstly, let's increase this PID control. Let's go to the 40%. And once I increase this output, because that is a cooling control, so the temperature will decrease. From this value, we will see the temperature is decreasing. And also, we can drag this window so that we can have an overall picture of this process change. This window size, we can adjust the range of this x-axis. Because this is the one cooling system, once I increase this output, so the temperature actually is dropping down. In the meantime, we can record, so as this time change, we change from 25 to 40%, and the temperature will change from 40 centigrade to basically now this value is working around 34. The system basically reaches a stable status. And now I will change this 40 to 15. And let's see what the behavior, what the change will be for this process value. Meantime, I will also record, so this time we change from 40% to 15%. I'm speeding up this video in 3 times, so we can quickly have an overall picture of this rising process. And in the meantime, we can also calculate this rising period. So roughly this entire rising period, that is the 40 or 50 seconds. So we have a rough idea every time we change this output, how long we will basically wait for this transition period. Alright, the system basically reaches a stable status. And from this time, and our control signal changed from 40% to 15%, and the temperature changed from 34 centigrade to 43 to 44 centigrade. The process, we change from 34 to 44 centigrade. And our control signal, we change from 40% to 15%. So we can calculate this gain of the process. That process has a 10-degree change, and the control signal gets a 25%. So we will have a rough idea what the gain of this process. Its sign should be a minus, that is cooling system. The gain of this process, that is a 0.4, which is true because if you recall, when we set up this simulated process, if we go back to this function block underscore process, when we set up the gain of this simulated process, the gain we set up, which is very close with our calculation. Things when we calculate this 0.4, the process has a noise, so it has a little bit off with this 0.42, but actually they are very close. And the reason why this gain that is a negative value, that's because that is a cooling system. And we introduced this topic in the previous video. And to deal with this is a minus. So from this PID program, we add this minus at this set point and this process value. That's because in the TcUtinity system, the gain of this PID controller, this gain, it cannot be a minus value. So an alternative way to set a minus on the gain, we can set a minus on this set point and process value. So this is the same idea. We set a minus value on the gain of the PID. Okay. And now the system is stable. So if we have an over picture, we can drag this window so we can see this whole change process. Okay. Based on this step response, we can use the Ziegler Nichols first method, step response method. We can draw a line and calculate that 2 times. And since in this process it has a noise, it's a little bit hard to draw that line. So I will prepare another transition time and it shows more clearly to draw that line. I will prepare the next transition rising edge. Meantime, please keep in mind the right line in this picture. This Ziegler Nichols method, it relies on this response, and the process response show as a first order system response. So we can calculate this 2 times. If your system doesn't show this step response like a first order response, you might need other method. Alright, to show this rising transition more clearly, I disable that noise at the beginning of this rising process. And based on this transition time, this process, let's calculate this again. From this transition time, that control signal changed from 25 to 10%, and the process changed from 40 centigrade to 46 centigrade. So through this process change, this gain still 0.4. So I will use this 0.4 as the KS value for this process gain. If we review the Beckhoff web page, so this KS will be used as a denominator to calculate the gain of this PID parameters. Okay, let's record the time at here and here. So let's go back to the TwinCAD train. Let's pause our train, zoom this area. Click this here and zoom this area. You can see this is the curve. We will basically draw a line at here. Basically, the line will touch at here. And at this end, so the line will touch at here. So this is the 25. And this line, that is a 50. So this time, that is a 25. From this point to this end, that is a 5. And the unit, that is a second. So if we go back here, follow this table, this time consistent of the control system, that is 25 seconds. And the TT, that is 5 seconds. And the KS, that is 0.4. Okay, so follow this table. We will calculate the K, Tn, and the Tv. So firstly, let's calculate Kr. The Kr, based on this equation, 1.2 times this Tis 25 and over 0.4 time the TT, that is 5 seconds. That equal to, that's 15. That's the gain. And then let's calculate this Tn. Tn equal to 2.0 times the TT. TT, that is 5 seconds. So that Tn is 10. TV, that is 0.5 times the TT, that is 5 seconds. So that is 2.5. So based on this Ziegler Nichols method, based on this table, we calculate the gain Tn and the TV. We can write those values into our initial parameters of the PID. And let's see what the behavior of this PID when the PID is working under the automatic mode. So let's go back to TwinCAD3, that PID controller area. So go back to control PID. So let me go to the offline. Okay, we will set the calculated value at here. The gain, that is 15. And the Tn, that is 10. And the TV, that is 2.5. Okay, 2.5, that is 2 seconds and 5 milliseconds. Okay, this TD, we will leave this 500 milliseconds as a default. And let's download this controller. And don't forget, we need to turn on this initiate so that we can set those PID parameters into the PID controller. And meantime, we will shift this controller into the automatic mode. Okay, let's click this login. When we click this login, we will download this new program to the controller. And meantime, this controller will not stop, so it will keep going. We can download this program on the fly. So log in with the online change. So we will not stop the controller. Currently, we haven't initiated this value, so it's still running the old value. So once we click here, double click, prepare the true, and click this write value. So we will write those values into the PID. And currently, this PID is working under the manual mode. So once we enable this initiate, so the PID will shift to the automatic mode. And in the meantime, let's prepare this side point first. And from here, let's set a 40. That is the side point of this PID. Okay, we set 40. We better also add this tag into this watch table so that we can set this side point. Okay. If we shift back to the scope, click this start record. So from this curve, we have a rough idea how that PID works. So now this process value is working around this green side point, but we have overshoot a little bit. Also because this process has a noise, so this output control is oscillating here. That means our PID gain that's a little bit high. We can decrease the gain. Also, because there's a little bit overshoot, so we can increase the integral value to decrease the integral influx. So let's go to the PID area. To do a fine tuning, we have this base value. Let's go to here and we can decrease this gain to 12. Also, we can increase this a little bit. For example, I can increase to 14. Derivative value to 1.5 because the process has a noise. And let's watch this online change. So this time, let's change the new side point from 40 to 30. So this is a new side point. and the right curve, that's the PID control. I'm using the 5 times speed to show this transition process. This is the current PID parameters, and these PID parameters are based on the Ziegler's calculation, and this is just a quick fine-tune. We will see this dark blue, this is the actual process value. There's no obvious overshoot. The actual control performance shows pretty good actually. Based on this presetting, this pre-calculation from the Ziegler Nichols setting rule, so we based on those parameters and we tuned a little bit, do a very quick commissioning. Process behavior shows very good. That means this Ziegler Nichols setting rule really works for this case. So if we quickly review, based on this control output change and step response process value change, we get a KS. Also, we give a system a step response. We calculate this time and this time. Based on this table, we calculate the K, Tn, and Tv. If you use the PI only, you will follow this rule here. Okay, let me start this display, and now let me set 40 again, and let's see this time change. I'm using 5 times speed to show this rising process change, this transition change. So from this area, we can also see the output already go to 0. That means the controller already tries best to increase this temperature. So once the temperature approach to this set point, the controller increases the output control. The controller adjusts this output under the automatic control mode. So we will see this process value reach this set point. And this system also includes the noise. All in all, this process behavior shows really good. And this control parameters basically can work for this process. Maybe the gain could decrease a little bit. That can make this PID output not so sensitive because this process has a noise. And we can pause this online and we can have an over picture at here. So from this over picture, we can see this is a decrease, this is set point, and this is the increased set point. And from these two times, the increased time and the overshoot, basically it looks very good. But from this area, we will see, because the system has a noise, the PID output is oscillating here. So that may not quite good for the actuator. So in the practice wheel, we can decrease the gain or tune the other parameters. For example, decrease the derivative value. To tune the PID gain, integral, and the derivative, we will discuss in the next video. In this video, we basically introduced how we can use the manual control to initiate a step response for our process. So we have a rough idea what the basic operating point of our process and what the behavior of our process. And based on the step response, and based on the Ziegler Nichols method, we can calculate the KS, this TS, and the TT. Those 3 values. And based on those values and based on this table, we can have a pre-setting for this gain, Tn and TV for this PID controller. Alright, that is the main topic in this video. See you in next video. I will show how can we tune the PID 3 parameters. See you in next video. Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.